Hello, student. Welcome back to this topic of magnetoelectric composites and their applications. So, already you have understood what is the meaning of piezoelectric effect and what is the meaning of magnetostriction effect, and you have understood what are the multiferroics or the magnetoelectrics, and with the help of this diagram, I have explained what is this magnetoelectric effect, and here we have shown the interlinking of the different fields when the two types of materials of different phase are mixed together. And these are the requirements for good ME composites, and we have seen the historical background of these ME materials. And there are two types of ME materials. One is the single phase material, and other one is the multi-phase material or the magnetoelectric composites. And this was the growth of the research field, that is the magnetoelectric composites field, shows the number of papers published during these years. And here we have understood how to prepare the magnetoelectric composites, and this is the auto combustion method, very versatile method. Gives the nano powders in a short period of time. And now I have to come to this a topic, that is the types of connectivity. So there are different types of connectivity. Connectivity in the sense, it is the connectivity between the two phases. How the two phases, that is the ferromagnetic phase and ferroelectric phase, are connected mechanically, and that is very, very interesting. So this is referred as the 0-3 connectivity. 0-3 connectivity. Here, what we have done is that one type of the particles of one type of phase are immersed in the lattice of the other. So both the phases are having the particle nature here. So what happens? Let us say these are the particles of the ferromagnetic phase. These ferromagnetic particles are embedded or immersed in the ferroelectric particles of the ferroelectric phase. So this is the case of bulk composites, where we are mixing of the powders of ferromagnetic and ferroelectric powders. When they mix together, it becomes the connectivity existed between the ferromagnetic phase and ferroelectric phase is referred as the 0-3 connectivity. And here next type of connectivity is the 1-3 connectivity. This is the 1-3 connectivity. Here what happens, 3 shows the dimension of the second phase. 3 show here, 0 shows the dimension of the first phase actually. So that means actually 0 indicates that the phase, the particles of the first phase are in nanoscale range. So that is the meaning. But the particles of the second phase are in the micrometer range. So that we are writing as a 0-3 connectivity. And here 1-3 connectivity, that means phase one material, which is the ferromagnetic material, is in the form of nanorods. These are all the nanorods. And these nanorods are embedded or immersed or inserted into the particles of ferroelectric phase, or into the lattice of the ferroelectric phase. So this is the 1-3 connectivity. One phase is made into the rods. Generally, they are referred as the nanorods, and since they are very thin, we are representing that phase as a 1, indicating that almost all one dimension like that. And the second phase is in the form of particles, so it is a 3-dimensional body. And so here you are immersing the nanorods into the this lattice of the ferroelectric phase. So then the type of connectivity existed in this case is the 1-3 connectivity. And next one is the 2-2 connectivity. This is a 2-2 connectivity. What is the meaning of 2-2 connectivity? Here you can see two slabs are there, two layers are there. So this is the first layer, this is the second layer. This is the first layer. Let us say it can be the layer of ferroelectric material, and this will be the layer of ferromagnetic materials, or vice versa. That means it can be the layer of ferromagnetic material, and this can be the layer of the ferroelectric materials. So these two layers are kept one over the another. Then here 2 indicates that the dimensionality. These are the 2-dimensional object. Actually, even though we have shown this much of thick here, actually they are in the form of thin films. So these are referred as the multi-layer thin films. So this is the first thin film, or that the second thin film is deposited, and the thin film is a substance which is having some length and breadth, but whereas the thickness is very, very small. So because of that reason, this type of object is represented as a 2. So it is a 2-2 connectivity. And one thin film is coated over the another, and then the type of connectivity existed between these two thin films is referred as the 2-2 connectivity. So this is another type of connectivity. And this connectivity sometimes it is referred as the non-epitaxial connectivity or the epitaxial connectivity. In case of epitaxial connectivity, there will be a matching of lattice of both the phases. That means both the phases, that is the ferromagnetic phase and the ferroelectric phase, should have the same lattice. That is called as the epitaxial type of connectivity. So matching of lattice will be there. In case of non-epitaxial connectivities, the lattices of the two different two phases will be of different type. That means the ferromagnetic material will have a different type of lattice, and the ferroelectric material will have the another type of lattice. Then there is a definite mismatch between the lattice of two phases, and that type of connectivity is called as the non-epitaxial connectivity. So this is another way of classifying the connectivity. One is called as the epitaxial connectivity, where there is a matching between matching of lattice is there between the two phases, and non-epitaxial means there is a mismatch between the lattice of two phases. And here Suppose you have prepared the sample in the form of multi-layer, then it will be a 2-2 type of connectivity. You will be having the 2-2 type of connectivity. And in this connectivity, how the measurements are made, that is depicted here. And this is called as the LL mode. This is a 2-2 connectivity, but this is referred as the LL mode. LL mode means it is a longitudinal mode. That means in this diagram, in this slab, what you are observing is that they are the slabs of ferromagnetic material, ferroelectric material, ferromagnetic material. 3 layers are there. So this ferroelectric material is sandwiched. This ferroelectric material is sandwiched between the layers of ferromagnetic material. So this M indicates the magnetization, P indicates the polarization, M indicates the magnetization. That means these layers are polarized or magnetized parallel to each other. Let us say they are magnetized or polarized along the x-axis. Then this is referred as the LL mode. That means I have in my earlier sessions I have explained about polling of the samples in electric field and magnetic field. So this magnetic layer is there, ferromagnetic layer. This is pulled in a direction horizontal to the direction of the applied external magnetic field, so that the magnetization produced in this layer is also parallel to the direction of the applied field. Then you will get the horizontal magnetization. Here also you have got the horizontal magnetization. That means the direction of the magnetic field will be horizontal. And here, this is the ferroelectric material. So during the electrical polling, this ferroelectric material is polarized in the x-axis. That means the applied electric field is in the x direction, and hence in that direction only the polarization is produced in this ferroelectric material. So that is why the polarization and magnetization are parallel to each other in this case, and this is called as the LL mode of the layers. This is second one is referred as the TL mode, that is transmission and longitudinal mode. So you can see very clearly in this diagram, the magnetization in the magnetic layer, ferromagnetic layer is in a transverse direction. Here also it is in transverse direction, whereas the polarization in a ferroelectric material is still in the longitudinal direction. So the magnetization is in transverse direction, whereas the polarization is in longitudinal direction, and hence this is called as the transverse longitudinal mode. This is the second mode. LT mode, longitudinal transverse mode. In this case, what is happened is that the magnetization in magnetic layers is in the longitudinal direction, whereas the polarization in the ferroelectric material is in the transverse direction, and hence this mode is referred as the longitudinal transverse mode. And the last one is the transverse mode. It is also very clear in this diagram that the magnetization produced in the magnetic layers is along the transverse direction, because the magnetic field applied to these magnetic layers will be in a transverse direction, and because of that reason, the magnetization in this magnetic layer is in transverse direction. Similarly, it is the case of ferroelectric materials, and this ferroelectric layer is exposed to the electric field, which is in transverse direction, and because of that reason, the electric dipoles present in this ferroelectric layer will align along the direction of the applied field, which is in the transverse direction. So, thus, in this case, the polarization is also in the transverse direction, and the magnetization in the magnetic layer is also in the transverse direction, and hence this is called as the transverse mode. So these are the different connectivities depending upon the application or applicability or the particular intention of the researcher. One of the connectivity will be used during the property measurement. So the piezoelectric constant D is represented as D. So how you are measuring this piezoelectric constant D? Accordingly, its mode is also defined. So this diagram again represents or indicates the cross-linking of the different fields and different parameters of the ferroelectric, ferroelastic, and ferromagnetic materials. And since a composite material will be having all these three properties at a time, it is called as the multiferroic. That means if a composite is having ferroelastic properties, ferromagnetic properties, as well as ferroelectric properties, then that type of composite is called as a multiferroic composite. And the coupling between ferroelectric phase and ferromagnetic phase is two types. Either it is strain mediated or it is stress mediated. So either strain or stress will be developed inside the composite material. Accordingly, one type of material will be activated, either the ferromagnetic material or the ferroelectric material. And here you can see ferroelectric material, the polarization in the ferroelectric layer is in this direction, whereas the magnetization in the magnetic layer is in this direction. They are all parallel to each other. This mode is called as a D33 mode. That means all are parallel, both magnetization and polarizations are parallel to each other. Under this condition, if you are measuring the ferroelectric constant D, then it is called as a D33 constant, or it is called as the piezoelectric constant measured in a D33 mode. And here you can see they are parallel, but one of the magnetization in bottom layer is opposite to that of the top layer, and if this is the case, this is called as D31 mode, and this is the D15 mode. Here all are in transverse direction. That means the magnetization in top and bottom layers and the polarization in the middle layer, they are all in transverse direction. And if this piezoelectric constant is measured in this condition, this is called as the D15 model or D15 model. So in here, I am going to explain the very important point of this topic, that is the measurement of ME voltage or magnetoelectric voltage. So the experimental arrangement of this ME setup, ME voltage measurement setup is as shown in this diagram. So here you are looking at electromagnet, this one and this one, they are the big electromagnets. that means to those actually they are the iron cores on which some copper wiring is wound and through which a current is passed, so that the magnetic field is produced by this cylindrical heavy iron pieces, and they are called as the electromagnets. So electromagnets are there. These are the electromagnets. These two electromagnets are connected to a power supply, a current power supply, and you can change the current passing through these electromagnets. Accordingly, you are changing the magnetic field produced at the center of these two coils. And the magnetic field produced by these two electromagnets will be at the middle, will be in the vertical, in the horizontal direction. Then here these two ring type of structures are the Helmholtz coil. These two are the Helmholtz coil, and through this Helmholtz coil, actually we are supplying the AC current. In these huge electromagnets, we are supplying the DC current to produce the DC magnetic field between these two poles, whereas we are supplying the AC current through this pair of Helmholtz coil, so that the magnetic field, produced by so that the field produced at the center of this Helmholtz coil is the AC field, AC magnetic field. So for the measurement of this MU voltage, we need both the fields, that is DC field as well as the AC field is AC field is AC field. So we are producing the both AC and DC fields. So these electromagnets produces the DC magnetic field because direct current is flowing through them, and this AC magnetic field is passing through this Helmholtz coil, and because of that reason, the magnetic field produced at the middle of this Helmholtz coil is the AC field. And the electromagnet and this Helmholtz coil are placed coaxially, so that at the center of this these electromagnets, both AC and DC fields are parallel to each other. And sample is a multi-layer sample is kept at the middle of this Helmholtz coil, and here a Gauss meter is there. This Gauss meter is used to measure the DC magnetic field produced by these electromagnets, and the AC field produced by this Helmholtz coil is calculated by making use of the number of coils in the Helmholtz coil and the amount of AC current flowing through them. And this function generator, ammeter, amplifier, and emitter are connected to this Helmholtz coil via this sample. And next, the voltage produced across this multi-layer sample at the top and bottom of this multi-layer sample is connected to the lock-in amplifier. And here this lock-in amplifier is required because the amount of voltage developed across the sample is very, very small. So in order to detect that small voltage, this lock-in amplifier will have to be used. So here actually from this lock-in amplifier, I am getting a VME, that means magnetoelectric voltage developed across the sample. From that measurement, I am going to calculate the magnetoelectric coefficient alpha E33. Alpha E33. This is a 33 because both magnetic and electric field are parallel to each other. So it is so it is referred as alpha E33 constant. Alpha E33 means this is the piezoelectric coefficient. So this magnetoelectric coefficient. This magnetoelectric coefficient alpha E33 is measured, is calculated by substituting the value of this VME, that is the voltage developed across the sample, and below it is divided by HC into T. That means AC field produced by Helmholtz coil is to be calculated, and to that the T means the thickness of the film is to be multiplied. So with the help of this formula, we are with the help of this formula, we are calculating the magnetoelectric coefficient. So this is a little bit complicated, but this experiment could be done successfully without any problem, and you can measure the ME voltage, magnetoelectric voltage across the sample, and then you can calculate the magnetoelectric coefficient with the help of this formula. And here just one example I am giving. We have done this measurement for this nickel copper ferrite, a tri-layer of nickel copper ferrite, PZT and nickel copper ferrite, and so here the magnetic field, DC magnetic field is also called as the bias field, is varied in this way, and along the y-axis, I have plotted the magnetoelectric coefficient calculated. So here that means we are changing the current DC current passing through this coil, so that we are changing the DC magnetic field at the middle of these two electromagnets. So the magnetic field produced at the middle of the two electrodes is in this range. So it starts from 50, 100 like that, and it goes up to 1000 oversted, and corresponding magnetoelectric coefficient estimated for this variation of magnetic field in the sample is shown for the different samples. So different samples are created because we are changing the composition of this ferrite material. That means if we, with the value of this X, the percentage of nickel and copper present in a particular ferrite is changing. So accordingly, we are getting some these 6 samples. So you can see here this magnetoelectric coefficient alpha increases like this slowly as the magnetic field is increased, and then starts decreasing. So this increase in the value of magnetoelectric coefficient is because of the increase in the ME voltage developed across the sample. Because here what happens, as the magnetic field is increased, what happens inside the sample? Because of the magnetostriction, more and more stress is created on the ferroelectric substance. So that ferroelectric substance accordingly develops the voltage, ME voltage. So because of that reason, stress is increased up to this level, and because of that reason, the voltage developed across the sample is also increased here. But beyond this limit, these curves are coming down because the saturation takes place. The saturation takes place. That means whatever the magnetostriction is there, it reaches its maximum value, and beyond that, what happens? The magnetostriction effect decreases because it doesn't follow the applied field. So because of that reason, the stress produced on the ferroelectric substance also decreases, and because of that reason, uh, the voltage developed across the ferroelectric sample is decreases, and hence the magnetoelectric coefficient also decreases. So this is just an example. So this experiment can be conducted for multi-layers or thick films or thin films, whatever it is, this experiment could be done. So in the in the next session, I am going to discuss on the different popular magnetoelectric composites, and uh, the amount of ME coefficient found in each case. Thanks for listening.